Hello everyone, and welcome to today's webinar, Tackling and Controlling Background Laboratory PFAS, the final part of Matt James's three-part series on PFAS. My name is Alex Nase from MacMod Analytical, and I will be moderating today's webinar. MacMod is a chromatography company that offers scientists innovative solutions for their complex separation needs. We recommend and supply the best columns and accessories to our customers. We also provide application notes, technical reports, white papers, and other up-to-date resources from industry-leading scientists to keep you informed. If you have any questions during the presentation, please type them in the chat window and include your name and company. We will answer as many questions as possible during the Q&A session at the end of the presentation. If you miss anything or would like to review the content, you'll be able to watch a recording of the webinar and view the slides on MacMod's website. We will also send out a follow-up email with links to the recording and slides. You can also find a collection of our past webinars and resources at macmod.com, including the first two parts of this series. And now I'd like to introduce our speaker today, Matt James. Matt earned his PhD at the University of Bristol, and over the last 15 years, he has worked within the technical support, applications, and R&D teams at Hychrome, now a part of Avantor. His recent focuses have included HPLC, UHPLC method transfer and translation, the use of solid core phases, development of next-generation LC stationary phases, and the development of LC methods for key applications such as the analysis of nitrosamines and PFAS by LC-MS-MS. Thank you for joining us today, Matt.
Thank you for the introduction, Alex, and welcome everyone. Thank you for joining us today for the final part of this webinar series. So today we're going to look at one of the more challenging aspects of PFAS analysis, and that is the occurrence of background PFAS contamination in the lab environment, how it can affect the results we obtain, and strategies for identifying and controlling it. We wouldn't be presenting this webinar without the kind support and collaboration from our US distributor MacMod. So once again, I just want to say a big thank you for hosting us today. For any inquiries following on from today's webinar or relating to chromatography in general, please feel free to contact their excellent support team. So in parts 1 and 2 of this series, we covered some of the background to PFAS analysis, the analytical methods used, and specifically how to go about developing LC-MS methods for PFAS analysis. In this final part, we're going to consider the issue of background PFAS in the lab environment and how we need to be cautious that this doesn't contaminate our samples. This is a topic that everyone who's involved in PFAS analysis will have experienced themselves. It's something that can vary considerably from lab to lab, even from operator to operator, and also from day to day. So it can at times be immensely frustrating. So hopefully some of the topics we're going to discuss will be helpful in your own labs. So in part 1, we discussed the immense usefulness of PFAS in various aspects of everyday life. And unfortunately, this usefulness also extends into the lab. So many materials and products we use could potentially contain PFAS. These PFAS compounds can potentially therefore be transferred into samples during analysis, leading to a significant possibility of accidental sample contamination with non-sample PFAS. In fact, obtaining blank blanks or blank laboratory reagent blanks can be one of the most challenging aspects of PFAS analysis. It's always important to remember that due to the very low detection limits mandated for PFAS, we're working at trace levels, so even very low-level contamination sources do have the potential to be problematic. So some of the potential sources of PFAS in the lab would include things like general lab consumables, so that's items such as lab vials, SP cartridges, filters, and centrifuge tubes. Solvents and reagents used in our experiments could potentially contain PFAS, and many lab instruments have PTFE components, which can be sources of PFAS, and this includes aspects of our LC-MS system. Our lab coats, along with clothing that we bring into the lab, could be potential sources, along with personal care products that we use as well. So items like lotions, cosmetics, and hand sanitizers could also be potential sources. The general lab environment, including work surfaces and air passing through the air conditioning filters, can potentially also be another source. So eliminating all possible sources of PFAS contamination is immensely challenging. Therefore, our approach must involve identifying the sources present in our own labs, taking steps to minimize their impact, and performing rigorous testing materials and chemicals. And by doing this, we can aim to achieve the low-level sub-part per trillion detection limits that are required for accurate PFAS analysis. In terms of the analysis of PFAS by LCMS, one of the most essential things we need to do is use the delay column, which we discussed last time. And really, this is so essential that I just want to spend a moment recapping this approach. So the potential presence of PFAS in lab solvents, buffers, and LC system components, so components like solvent lines and bottles, can lead to contamination. In a standard LC setup, PFAS from the mobile phase, the degasser, pump, mixer, or injector can accumulate on the column head during column equilibration. Then when we start our gradient run, these PFAS that are built up can elute from the column and are detected by the mass spectrometer. When an actual sample is injected, these background PFAS co-elute with our sample PFAS, leading to inaccurate quantitation. And this is evident in chromatogram A, which is a blank run, showing a PFOA peak from the LC system, and chromatogram B, where the background peak then overlaps with our sample peak. To resolve this, a delay column, which is rather unique to PFAS analysis, is installed immediately before the sample injector. The delay column traps PFAS from the mobile phase, eluting them separately from the sample piece. And this is shown in chromatogram C with the delay column and chromatogram D, where the sample is injected with the delay column installed. And here the background PFOA peak is well separated from our sample peak, which allows us to accurately quantify the target compound. The use of a PFAS delay column is essential to prevent false positives and ensure accurate analysis. The LCMS run is, of course, just one part of the entire workflow, and we clearly also need to carefully consider sample handling and sample preparation processes. We can reduce the potential for sample contamination by following a few general tips. So firstly, it's crucial to avoid using PTFE and any fluoropolymer-containing materials in our workflows. Additionally, it's advisable to steer clear of detergents and glassware washers. Instead, I'd recommend dedicating glassware such as mobile phase bottles and other equipment like pipettes specifically for PFAS analysis rather than using any communal equipment wherever possible. We should also replace glassware and consumables that actually come into contact with our samples with those made from polypropylene. Now, this isn't so much a contamination issue, but rather that PFAS in samples and standards can absorb onto glass, making polypropylene a better choice for many PFAS analysis procedures. If possible, set aside a dedicated area of the lab for PFAS analysis. Some organizations even go as far to establish dedicated PFAS labs. It's also essential to establish protocols to regularly test new batches of consumables and solvents to ensure they're clean and suitable for use. So in testing reagents and consumables, we should use numerous blanks and no injection blanks to confirm that any contamination we do observe originates from the material being tested and not from somewhere like the LC system. We can also pre-clean consumables before use. I tend to pre-clean things like sample reservoirs, sampling bottles. For consumables like vials and pipette tips, we need to test those to find ones that are suitable for use. And this means we can potentially avoid the need to pre-clean these sort of items, but I certainly know that some do take the approach of pre-cleaning all consumables with suitable organic solvents before they're used for PFAS analysis. The key here, I think, is really to identify what processes work in your lab and for your specific application. Following thorough and methodical work practices is key, so keeping the lab organized, working on cluttered spaces, and regularly changing things like gloves throughout the day to reduce any potential for cross-contamination. We should also avoid using waterproof or outdoor waterproof clothing, as these can potentially be treated with PFAS-containing substances. It's worth mentioning here that sample collection in the field is another topic which is somewhat beyond the scope of today's talk, where we also need to carefully consider our processes. But in terms of the lab, by identifying and implementing processes that work for your lab, you can significantly reduce the potential for sample contamination. So when we first started working with PFAS, we realized it was crucial to identify potential sources of PFAS contamination with our own lab. And to do this, we began testing various products and materials that we suspected could contribute to contamination. This approach was beneficial as it allowed us to modify workflows and remove materials that could potentially contaminate our samples and help us to troubleshoot any future issues. To test materials, we follow a pretty straightforward procedure. We place the sample we want to test in a clean centrifuge tube and add a milliliter or two of 96% methanol and 4% water. If we want to quantify the analysis, of course, we can also add an internal standard. Then we vortex for 30 minutes and test using LCMS. Of course, this procedure can be adapted to fit the needs of your own labs. On the chart to the right, you can see examples of materials we tested. So sticky tape and white tape, which we use typically extensively for labeling samples, were not surprisingly found to contain detectable levels of several PFAS. Things like sticky notes also gave a positive hit, and so suggesting that avoiding any sort of sticky substances might be a general good rule of thumb. Latex gloves and some marker pens can also be sources of contamination, and tinfoil is another material which is quite widely used, and I've certainly heard a lot of analysts say it should be avoided or at least solvent cleaned before use. And indeed, in our tinfoil that we had available, we found small levels of PFBS and PFOA as well. One source I found quite interesting in our lab was lab tissue, which we quite often use for various purposes. These are, of course, made up from recycled paper. And so what we actually found is that not only did every sample we test contain extractable PFAS, but the distribution of PFAS varies quite considerably, presumably due to differing content within the paper being recycled. So these are obviously all potential sources of extractable PFAS that, if we're not careful, could potentially contaminate the environment we're working on our samples in if the samples come into contact with them. Whilst it's not easy to necessarily eliminate those materials from lab, we can certainly look to restrict or control their use to minimize those risks. So, of course, it's absolutely essential that any consumable products that come into contact with our samples are free of detectable PFAS, as they can immediately contaminate our samples. Therefore, it's crucial to routinely test consumables on a batch-to-batch basis. For example, whenever a new batch of sample vials or pipette tips arrives or a new pack of vials is opened, it's always worth testing a few before using them in the workflow just to verify they're clean. It's important to test these consumables in a way that accurately reflects their use in the workflow. So, for instance, considering centrifuge tubes in a method like EPA 537.1, these tubes collect 8 mils of 96% methanol, which elute from the sample from the SPE cartridge. This is then blown down to dryness using nitrogen and reconstituted for analysis. So to test the cleanliness of these tubes, we could take 8 mils of our elution solvent, place it in a centrifuge tube, vortex it, blow down, reconstitute and analyze as we do in the full analytical procedure. There are other potential ways to test as well. So for example, in an EPA 537.1 separation, we use 1 microliter injection. For testing consumables, it's feasible to increase the injection volume tenfold to 10 microliters. This increases the sensitivity of the analysis, although it may compromise peak shapes for early eluters. However, for screening processes, this is quite a reasonable approach. Pipette tips are crucial as we use them to transfer our samples. We test these by pipetting 96% methanol into a clean vial and analyzing it by LCMS. Sample vials are tested similarly. I tend to vortex mix them before analysis to ensure the solvent contacts both the vial and the caps, as this could happen with your samples. Using a higher injection volume for this type of testing gives us a better snapshot of the potential PFAS composition and greater confidence that our pipette tips and vials are free from PFAS. It's important to note that the term PFAS-free can be a bit misleading because we typically test for only a small subset of PFAS. When we say something is PFAS-free, we basically mean we can't detect the specific PFAS we're looking for. There could, of course, be other PFAS present that our LCMS method doesn't pick up. So therefore, if you expand the range of PFAS you're analyzing or begin working with a new method, you need to rigorously test for those new PFAS compounds and not just assume that what was PFAS-free with one method is PFAS-free with another. So here's an example of why it's crucial to test things like sample vials before we use them in our workflows, even if they're recommended for PFAS analysis. In this case, we examined polypropylene sample vials with a polyimide cap, which were recommended for PFAS analysis. However, when we added methanol to the vial and performed an injection, we observed a significant peak corresponding to a donor. Tracking contamination in consumables requires a systematic step-by-step approach. So firstly, we checked our no injection blanks, which confirmed that the LC system was functioning correctly. We also performed an injection from an empty sample vial, shown in the pink chromatogram, which indicated that our autosampler was also fine. This confirmed that contamination was not coming from the LC system, but the actual sample in the vial itself. When we replaced the polyimide cap with a polypropylene cap from a different vendor, the peak disappeared, indicating that the polyimide cap was the source of the contamination. And then finally, confirmation at the top shows that multiple polypropylene vial sources with that particular cap are suitable. So this is an example of what we're looking for with these kind of tests. These are vials that we currently use in our lab. We launched these in Europe last year, and they're specifically designed for PFAS analysis. And as you can see from the data shown on this page for a range of 18 PFAS, these are completely free from any background PFAS for this method. Of course, as I mentioned, we tested these using a 10 microliter injection volume, so we're testing their cleanliness at well below the level that we would cause an issue within our analytical workflow. And we recently moved on to extend our methodology to monitor additional PFAS compounds via a different method, EPA 533. And again, with this testing protocol, we didn't detect any background PFAS, which gave us additional confidence with using these vials. So one of the steps in our analysis with possibly the highest potential for sample contamination is sample preparation. So a common form of sample preparation, one of the simplest forms, is the use of syringe filters to remove particulates from the sample, which is particularly applicable to things like environmental water samples. It's crucial here to use high quality filters and choose appropriate filter materials. So for instance, EPA 1633 recommends using nylon filters and advises against using filters containing PTFE. Here we've got an example of 3 different PTFE filters, all of which we found to contain various levels of several PFAS. Regardless of the filter used, it's wise to consider pre-washing the filter before you actually use it. So syringe filters can be tested by eluting the filter with 2 mL of a suitable organic solvent, such as methanol, and then analyzing it by LCMS. Additionally, it's important to test the syringe itself. We recently encountered contamination from syringes with a black polyisoprene stopper, which contaminated our solvent with a donor. As we discussed in the previous webinar, many sample prep protocols utilize solid phase extraction. Typically, this is carried out using a manifold or column processor like the one shown in the picture. Now, because we're performing sample pre-concentration, any background PFAS from this equipment or solvents can be amplified using this approach. The vacuum extraction manifold is one piece of equipment that we really need to be particularly cautious about, as PTFE is quite commonly used in some of the manifold components in the sample flow path, such as needles, stopcocks or taps, and connectors. In many cases, these can be replaced with polypropylene equivalents to make them PFAS compatible. A good precaution is to thoroughly pre-clean the collection chamber, any flow channels, and any sample reservoirs or tubing used to transfer large volume water samples to the SPE cartridge, regardless of the manifold used. The extraction manifold we use is entirely fluoropolymer free, and using this manifold, we were able to obtain very clean laboratory reagent blanks for EPA method 537.1 as shown in the chromatograms on the screen. Incidentally, the 2 peaks in the bottom right are internal standards and not PFAS. At this point, I just want to cover a quick cautionary tale from when we moved on to look at a wider range of PFAS. As I mentioned, when we initially worked with EPA 537.1, which tests for 18 PFAS compounds, we obtained nice clean blanks using the defined SPE procedure. However, when we began working with EPA 1633, which includes an expanded set of 40 PFAS, we found that our blanks contained a high level of 6,2-fluorotellumer sulfonic acid. By testing various stages and components of the workflow, we quickly found that this was originating from the SPE manifold. To further assess this, we then examined the individual manifold components in the flow path, so the lure fittings, the taps, the flow needles, and that even though these were all manufactured from polypropylene, so on the face of it should have been suitable for PFAS, It was the taps that gave a big hit for this particular PFAS. We found that through use, the level dropped, but that despite cleaning with sonication, the contamination persisted at a high level and we couldn't fully remove it. The taps are a one-piece design that couldn't be disassembled, so we assume that perhaps a release agent or a lubricant is present within the tap barrel from manufacture, which is continuously transferred when the tap is turned during use, hence why we aren't able to remove it effectively through cleaning. We also found that the other fittings showed low levels of contamination through being in contact with the taps, which then required extensive cleaning to remove. In the end, we were able to switch to alternative polypropylene taps from an alternative source, which were found to be clean. So advice here is really that to be aware of that even components that we think will be suitable can contain some hidden surprises, and that if you have an approach that works for one set of PFAS components, beware that if you expand your analysis to monitor additional PFAS, additional sources of contamination may appear that you weren't originally aware of. So another step of the sample preparation protocol that I personally had considerable trouble with was the sample blowdown step. So to test our nitrogen blowdown equipment, we used a simple protocol, blowing down 8 mils of methanol to dryness with nitrogen in a 10 mil polypropylene transfer tube, which was then reconstituted in 1 mil of methanol and analyzed by LCMS. What we found was that regardless of the position that we used in our nitrogen blowdown equipment, our samples were consistently contaminated with PFHXA. This level of contamination remained consistent over time. And when we considered it, we had several potential sources of this contamination. So it could originate from the blowdown rig itself, or it could originate from the nitrogen source, which in our case was a nitrogen generator, which of course contains numerous components such as filters. So we conducted several experiments to try and pinpoint the source of contamination. So firstly, we removed the blowdown rig and simplified the setup by attaching a glass pipette to our nitrogen line. We found that this didn't solve the problem, but it confirmed that the nitrogen blowdown rig itself was not the source of contamination. Rather, it was the nitrogen supply. Next, we tried using an activated charcoal trap to try and clean the nitrogen supply, but this had no impact. So our nitrogen generator was actually fed from a compressed air supply located at the other end of the building, and it was delivered. This compressed air was delivered via a long network of nylon gas lines running through the ceiling. When we extracted a piece of this nylon tubing in methanol, we detected PFHXA, so that indicated that the gas line tubing itself was potentially causing the issue. We assessed several other types of tubing made from different materials, which included polyurethane and two sources of PTFE. Ironically, the PTFE tubing was actually the cleanest, but remembering we were only testing for 18 PFAS at that point, we preferred not to use it in the interest of forward compatibility. The solution we found was to move a nitrogen cylinder into the lab and connect it to our blowdown rig using PVC tubing. Although the PVC tubing also actually contained PFAS, we found that siphoning methanol through the tubing eliminated the contamination. We assume that PFAS contamination originated probably from a substance that was used during the tubing's manufacture. So using this new arrangement, we were then able to perform the analysis without contaminating our samples during the blowdown step. So one final potential source of contamination I want to touch on is the solvents and reagents such as buffers, acids, and bases that we use in our analysis. Solvents are often one of the most discussed and can be one of the most frustrating sources of background contamination PFAS analysis. Many analysts have reported significant batch-to-batch variation in background solvent PFAS levels, or have had difficulty finding solvents and reagents that are suitably clean for use. So the general recommendation is to always use the highest grade solvents and reagents possible, such as LCMS grade. Recently, some manufacturers have also introduced PFAS grade solvents, which are typically batch tested to conform with PFAS testing methodologies. It's essential to always test newly received solvent batches before using them. So personally, I do a quick test of any newly opened bottles with an increased injection volume, like we discussed earlier, to ensure that the new bottle is clean. When testing organic solvents, it's important to replicate their use in the workflow. So this can be done by either blowing down a volume of solvent and reconstituting it to replicate the workflow, or using a large volume injection, as we discussed a moment ago. Testing aqueous solvents and buffers is a bit more involved since they're typically used in the sample prep procedure. There may be some possibility to do large volume injections, potentially up to a milliliter. And I've seen direct inject methods where analysts use such injection volumes. But another option, of course, is to process those aqueous solvents as per the PFAS analysis protocols. And in methods such as the EPA methods, that's typically covered by our solvent reagent blanks. In Europe, we've recently launched a range of PFAS-grade solvents, including methanol, acetonitrile water, and 5 millimolar ammonium acetate premix mobile phase. The chromatograms on the left show the impact of these solvents when used as the mobile phase. So compared to LCMS-grade solvents, the PFAS-grade solvents result in a much lower levels of background PFAS accumulating on our column. Additionally, for some PFAS, we observe less baseline noise as well, which improves the signal-to-noise ratio of our analyte peaks. Using a 10 microliter injection volume, we've tested these solvents with our EPA 527.1 method, and this approach achieved limits of detection in the very low single-digit parts per trillion level directly on the solvents without any sample pre-concentration. We've also taken these solvents through the full EPA protocol and obtained very clean laboratory reagent blanks for that method. So I'd highly recommend assessing whether PFAS-grade solvents can improve your own PFAS analysis. To conclude, over the course of these 3 webinars, we began with a look at some of the background to PFAS analysis, particularly in drinking water, and how the very low level detection limits required necessitates the use of LCMS. And from there, how we go about developing suitable LCMS methods. In general, a C18 phase using ammonium acetate buffer with either methanol or acetonitrile as the organic modifier tends to be a good starting point. An essential part of the instrument setup is, of course, the use of that delay column to deal with background PFAS derived from the instrument itself. We've then today gone on to discuss how, because of the low levels we're working at and the ubiquitous presence of PFAS, the potential sample contamination within laboratory workflows is a serious concern for PFAS analysis. Key approaches to mitigate the risks of this include identifying and eliminating or controlling the use of materials containing extractable PFAS, the use of appropriate consumables and equipment, and continual testing and monitoring of those consumables. Maintaining good working practices and cleaning procedures is also important, and that the use of high-grade solvents and reagents and continual experimental monitoring of their quality is also important. And finally, just that cautionary note that if you have workflows set up that work for you but extend the range of PFAS you're looking to monitor, just be wary that there may be a degree of work necessary to remove background sources that you weren't previously aware of. So to finish, just a reminder of the various technical materials that we have available. These can all be downloaded from MacMod's website. And finally, thank you for your attention over the course of this webinar series. I hope that the content proves useful for you. And I'm happy to take any questions we have now, or otherwise for any further assistance, please do feel free to get in touch. Thank you.
Thank you, Matt, for an incredible presentation and a conclusion to our PFAS series. We will now move on to the Q&A portion of the webinar. I just want to remind you to please type your questions into the chat window and include your name and company, just in case we aren't able to get to all questions. We are able to follow up with you. Okay, so first question, Matt. Why do we need to worry about solvent purity if the delay column traps the background PFAS?
Yeah, it's a good point. There is obviously an argument that why do we need to worry if any PFAS in the solvents we use to make up a mobile phase are trapped by the delay column. we did, when we use higher quality solvents, we do tend to see less baseline noise, which can help with the signal to noise for your analysis. But probably the key thing to consider there is that we're also using those solvents in our sample prep procedures as well. So things like, in the case of water samples, buffers such as ammonium acetate may be added to the sample themselves. And we also use various extraction solvents, which then, if we're using SPE, we then, or nitrogen blowdown to pre-concentrate, you're actually, any impurities that are in those solvents are going to be concentrated through the workflow. So even though on the face of it, in terms of mobile phase, certainly the delay column will do a lot of the work for you, and maybe it's not such a concern, it's still very important to consider the purity of the solvents and reagents we use in the actual sample prep side of our workflows as well.
Okay, thank you. Next question. Can plastics other than polypropylene be used in PFAS workflows?
There's high density polyethylene is another plastic that we do tend to see a bit with some consumables, but it does tend to be polypropylene is what's generally recommended for PFAS analysis. I guess what I would sort of say really is if there are any other materials that you're looking to use or may have a necessity to use, perhaps, again, that sort of rigorous testing, just making sure that you sort of try extracting that material and just try and get a feel for any PFAS that are in it is very important, so it doesn't compromise the analysis. So yeah, it's possible to use other materials, but it tends to be polypropylene and high density polyethylene that tend to be available for you to use with a lot of the consumables, I would say.
Okay, and I think we have time for one more question. Can water from a water purification system be used for PFAS analysis?
We personally do use a water purification system to make up mobile phases and also to prepare our laboratory reagent blanks for some of our water testing methods. Again, what I would say is it would be important to verify with the purifier manufacturer as to whether there are potentially any PFAS containing components or fluoropolymers within the water purification system that could be a concern. So it would certainly be worth contacting them. And of course, if you do use a water purification system, just making sure that you're rigorously testing the water that comes from that system. But certainly there are purification systems out there that are suitable for use, and we ourselves do use one in our own lab as well. So yeah, they certainly can be used.
Okay, unfortunately, that is all the time we have for today. If you did have a question that we did not get to, we will follow up with you via email sometime next week. We will also be sending out a follow-up email with a link to the recording and the slides, and they will also be available on our website. I want to thank you all for joining us for the third and final part of Matt's webinar series, and also thank Matt himself for giving us his time to present these three parts of the series. We hope these sessions have provided valuable insights that you can bring back to your lab. Before we wrap up, we'd also like to invite you to the next chapter, or our next webinar, Beyond Chemistry, Choosing the Right HPLC Column for the Real World, featuring Dr. Lee Polite from Axion Labs. The session will take place on July 31st at 2 p.m. Eastern and promises to deliver expert tips for making smart column choices in real-world applications. Look out for registration details in our follow-up email. And once again, thank you for joining us today. We hope to see you at future webinars. Have a great day.